Welcome, everyone. Today, we are diving into the core mechanisms that make cloud computing incredibly powerful. Let's get started. Welcome, everyone, to this essential training session. Today, we are exploring the fundamental pillars of cloud computing, focusing specifically on high availability and scalability. If you have ever wondered why businesses are migrating away from traditional on-premises data centers, the answer largely lies in these two concepts. Let us start with the basics. What exactly are we talking about? High availability, or AHA, is all about ensuring that your applications and IT resources are accessible whenever your users need them, regardless of unexpected hardware failures or network disruptions. On the other hand, scalability is the system's ability to dynamically adjust its computing resources to meet fluctuating user demand. Why does this matter? Because in a traditional setup, you must purchase enough hardware to handle your maximum potential traffic, meaning you overpay for idle servers most of the year. In the cloud, the consumption-based model allows you to pay only for what you use. We will take a deep dive into how these mechanisms work, how you configure them, and when to use them to create a resilient, cost-effective infrastructure. Let us take a look at the diagram on your screen. It visually breaks down the core benefits we just discussed. At the top, we have the overarching umbrella of cloud services benefits. You can see it branching off into our two main focus areas for today, high availability on the left and scalability on the right. Notice how high availability flows directly into continuous uptime and fault tolerance. This represents the cloud's ability to keep your business running even when physical hardware fails. On the right side, scalability flows into dynamic resource adjustment and cost efficiency. This highlights how the cloud automatically matches your infrastructure to your current user demand, meaning you are not wasting money on idle servers. Ultimately, both of these pathways converge at the bottom into a single, critical goal: business continuity. Whether you are protecting against a sudden server crash or a massive, unexpected spike in customer traffic, both high availability and scalability work together synergistically to ensure your business operations never miss a beat. They are truly two sides of the same coin. Now that we have the big picture, let us zoom in on high availability. At its core, high availability is the strategy and implementation of maximizing your system's uptime. The cloud natively supports reliable infrastructure through a decentralized design. Cloud providers like Microsoft Azure back this up with financial guarantees known as service level agreements, or SLAs. For instance, you might see an SLA of 99.95% uptime for properly configured virtual machines. But why is this so critical? Because in the modern digital economy, downtime equates to lost revenue, diminished customer trust, and severe operational bottlenecks. We achieve high availability through absolute redundancy, meaning we deliberately eliminate any single points of failure in our architecture. If a hard drive fails, a power supply blows out, or a network switch goes dark, another redundant component instantly takes over. Going deeper, high availability does not just protect you from unexpected disasters like hardware crashes, it also protects your applications during planned, routine maintenance, ensuring your users never notice when the cloud provider updates the underlying host operating systems. Look at the flowchart presented here to understand how a highly available system routes traffic. On the left, we start with the incoming user request. Instead of hitting a single server directly, which would be a massive single point of failure, the request hits a load balancer, highlighted in pink. The load balancer is the intelligent traffic cop of your architecture. It constantly monitors the health of the servers sitting behind it. You can see it actively routing traffic to server instance 1 and server instance 2. These servers are running in an active state, sharing the load. Now, look at the dotted line pointing to server instance 3. This represents our failover redundancy. If server 1 suddenly loses power and drops offline, the load balancer instantly detects that the server is unhealthy. Without any human intervention, it stops sending traffic to the dead server and immediately reroutes those users to the remaining healthy servers, or activates the standby instance. This seamless transition is the very essence of high availability in action. Let us explore the specific mechanisms the cloud uses to provide high availability. How do we actually separate our resources to avoid outages? We use isolation boundaries. First, we have fault domains. A fault domain represents a physical rack of servers that share the same power source and network switch. If a power unit shorts out, everything in that fault domain goes down. Next, we have update domains. When the cloud provider rolls out patches, they only reboot one update domain at a time. By placing your virtual machines into an availability set, the cloud platform automatically distributes your VMs across multiple fault and update domains. But we can go even bigger. What if an entire data center catches fire or loses power? That is where availability zones come in. Availability zones are physically separate data centers within the same geographical region, complete with their own independent power, cooling, and networking. By distributing your application instances across different availability zones, you ensure that a catastrophic failure in one physical building does not take your application offline. For absolute maximum resilience, you can even replicate across paired geographic regions. This diagram brilliantly illustrates the concept of availability zones within a single cloud region. At the top, we have the overarching cloud region, which is a broad geographical area like East US or West Europe. Beneath that, the region is divided into 3 distinct availability zones: Zone 1, Zone 2, and Zone 3. Notice the specific traits attached to each individual zone. They each point to their own independent power and cooling nodes. This is the crucial takeaway. These zones are not just separate rooms in the same building. They are distinct, physically isolated data center facilities located miles apart from one another, yet connected by ultra-high-speed, low-latency fiber optic networks. If a flood, a local blackout, or a network fiber cut severely damages availability zone 1, the infrastructure in zone 2 and zone 3 remains completely unaffected. As a cloud architect, if you deploy copies of your database and web servers into all 3 of these zones, your application essentially becomes bulletproof against localized physical disasters. This is how enterprise-grade high availability is structurally designed. Transitioning from availability, let us now focus on our second major pillar, scalability. While high availability ensures your system is always running, scalability ensures your system always has the exact amount of computing power it needs to perform well. Scalability is defined as the ability to dynamically adjust your allocated resources to match your current user demand. Imagine you run a retail website. Traffic is low at 3 a.m., but spikes massively at noon. In a traditional data center, you have to buy enough servers to handle the noon spike, meaning those servers sit idle and waste money at 3 a.m. Scalability solves this problem. It allows your infrastructure to expand and contract on the fly. Why is this revolutionary? Because it completely eliminates the need to guess your capacity requirements. It prevents your systems from becoming overwhelmed and crashing during unexpected traffic surges, while simultaneously saving you money during quiet periods. This is the heart of the cloud's consumption-based, pay-as-you-go model. You are literally only renting the exact amount of CPU and memory you need, exactly when you need it, ensuring highly predictable performance and cost. Let us interpret the sequence diagram to see the temporal flow of scalability. We have 2 actors here, user demand on the left and cloud resources on the right. The sequence starts with a low-traffic event, such as nighttime hours when users are asleep. The cloud resources intelligently respond by scaling down. This action directly saves the business money because fewer servers are running. Then, the scenario shifts. A high-traffic event occurs, perhaps a daytime spike or a marketing campaign launch. The cloud resources detect this surge and immediately respond by scaling up. More servers or compute power are rapidly provisioned to absorb the load. This ensures that the end users experience zero lag and the application maintains peak performance. This continuous, elastic conversation between demand and resource allocation is what makes cloud scalability so incredibly powerful. It is a fully automated dance that perfectly balances operational performance with financial efficiency, removing the human guesswork from infrastructure management. When we talk about scaling in the cloud, it is critical to understand that there are 2 distinct directions you can go: vertical scaling and horizontal scaling. Let us define both. Vertical scaling, also known as scaling up or scaling down, focuses on changing the capabilities of an existing resource. If your virtual machine is struggling, you vertically scale it by adding more CPUs or more RAM to that specific machine. It is like upgrading the engine in your car to go faster. However, vertical scaling has limits. Hardware can only get so big, and it often requires a reboot, causing brief downtime. Horizontal scaling, on the other hand, is known as scaling out or scaling in. Instead of making one machine bigger, you add more machines to the pool. If one web server is overwhelmed, you simply spin up 5 more identical web servers and use a load balancer to distribute the traffic among them. Why choose one over the other? Legacy databases often require vertical scaling, but modern, cloud-native applications overwhelmingly favor horizontal scaling. Horizontal scaling provides virtually limitless capacity and perfectly complements the high availability concepts we discussed earlier. This flowchart clearly breaks down the taxonomy of scaling strategies. From the top, we diverge into our two main paths. On the left branch, we have vertical scaling. You can see this splits into scale up by adding CPU or memory to an existing machine and scale down by removing them. Remember, vertical scaling modifies the size and power of a single instance. Now, look at the right branch, horizontal scaling. This splits into scale out by adding completely new virtual machine instances to your environment, and scale in by terminating unused instances. Horizontal scaling changes the quantity of your resources, not their individual size. In an enterprise cloud environment, you will rely heavily on the right side of this diagram. Tools like virtual machine scale sets are specifically designed to automate the scale-out and scale-in processes based on real-time metrics. By understanding this visual distinction, you can better architect your applications to be elastic, allowing them to stretch horizontally across the cloud fabric when user demand surges. To truly harness the power of horizontal scaling, we use a feature called autoscaling. Autoscaling is the intelligence engine that completely automates resource management, removing the need for a human engineer to manually add or remove servers. How does it work? You start by setting strict boundaries, a minimum, a maximum, and a default number of instances. This ensures your application always has a baseline of availability, but also guarantees you won't accidentally spin up 1,000 servers and drain your IT budget. Within those boundaries, you define scaling rules. These can be metric-based, such as instructing the system to scale out by 2 instances if the average CPU utilization exceeds 80% for 10 minutes. Alternatively, they can be time-based, allowing you to proactively scale out every Monday morning at 8 a.m. before the employees log in. A critical deep dive concept here is the cool-down period. When the system scales, it needs time for the new servers to boot up and absorb traffic. A cooldown period forces the autoscale engine to wait a few minutes before scaling again, preventing a chaotic loop of rapidly adding and deleting servers known as flapping. Let us walk through this state diagram to see the precise life cycle of an autoscaling event. We begin in the monitoring metric state, where the cloud platform is constantly checking the health and load of your application. Suddenly, traffic spikes, moving us along the arrow to threshold exceeded in this case. CPU usage has jumped above 80%. The system immediately triggers a scale-out action, automatically deploying 2 new server instances to handle the load. But critically, look at the next step, the cool-down period. The system deliberately pauses for 5 minutes. It waits to see how the new servers affect the overall CPU average before making any more decisions. This prevents over-provisioning. Once the cooldown ends, we return to monitoring metrics. Later, when the users log off, we hit the threshold dropped state as CPU falls below 30%. The system executes a scale in action, removing a server to save money, and again enters a cooldown period. This elegant, automated loop ensures your infrastructure is always perfectly right-sized, minute by minute. Let us tie all these concepts together with a highly critical, real-world use case, an e-commerce platform preparing for a massive Black Friday sales event. This is a high-stakes scenario where downtime literally costs millions of dollars per minute. The threat is twofold. First, an unprecedented tsunami of global user traffic that could overwhelm the servers. Second, the ever-present risk of a physical hardware failure in the data center at the worst possible moment. How do we solve this? We combine high availability and scalability. For the traffic spike, we configure our front-end web servers in a virtual machine scale set with aggressive autoscaling rules. As the marketing emails go out and shoppers flood the site, the scale set automatically detects the CPU load and horizontally scales out, seamlessly adding dozens of web servers. Simultaneously, to address the hardware threat, we have deployed our backend customer database using a zone-redundant configuration. If the power supply to the primary database rack actually blows out under the heavy load, high availability instantly fails over to a secondary database in a completely different physical availability zone. The customer clicking checkout never even notices a glitch. This architectural flowchart demonstrates our Black Friday solution in action. At the very top, we have our global shoppers generating massive traffic. This traffic hits our global load balancer, the intelligent gateway to our system. The load balancer routes requests down into the auto-scale web tier. You can see WebVM1 and WebVM2 handling the initial load. But notice the dotted line automatically adding WebVM3 through N. This is our horizontal scalability working in real time to absorb the Black Friday rush. Now, follow the arrows down from all those web servers into our data layer, the zone redundant DB. This is where high availability shines. The database is actively running in Zone 1, but it is continuously synchronizing data to a standby database physically located in Zone 2. If Zone 1 catches fire, the system automatically redirects all those web servers to the standby database in Zone 2. By combining the elastic expansion of the web tier with the rigid fault tolerance of the database tier, we have constructed an enterprise-grade cloud environment that can survive both astronomical demand and catastrophic hardware failure. As we wrap up our training, let us look at the big picture and summarize the synergy between high availability and scalability. Throughout this session, we have treated them as distinct concepts and structurally, they are. High availability is your shield. It protects your application against unexpected infrastructure and hardware failures. Scalability is your engine. It protects your application against overwhelming spikes in user demand, while also throttling down to save you money when demand drops. However, true cloud mastery comes from recognizing how they intertwine. By architecting your systems so that the front-end web servers can scale horizontally via auto-scaling, and your back-end databases are highly available and replicated across multiple physical availability zones, you achieve a state of ultimate resilience. Together, they provide predictable performance, optimized financial costs, and an unwavering level of trust from your end users. This holistic approach is the very foundation of what Microsoft calls the well-architected framework. It shifts IT from being a static, fragile cost center into a dynamic, automated asset that drives business success. Thank you for your time today. Let us conclude with this final synthesis diagram, reading it from the bottom up to see how these foundational elements build toward ultimate success. At the base, we have the core capabilities we have mastered today: fault tolerance and elasticity. Fault tolerance is the driving force behind high availability, ensuring your systems survive hardware disasters. Elasticity is the driving force behind scalability, allowing your infrastructure to stretch and shrink on demand. Both of these pillars support the critical business outcomes in the middle layer: performance predictability, meaning your app is always fast, no matter the load, and cost optimization, meaning you never pay for idle hardware. When you achieve these two outcomes through HA and scalability, you reach the pinnacle of the diagram: cloud success. Notice how all of these elements are bound together by the well-architected framework at the bottom. This framework is the philosophy that dictates that building resilient, scalable systems is not just an IT task, but a fundamental business strategy. Keep this diagram in mind as you design your future cloud environments.